Continuing in this series of videos, examining physics, really, just as it is, as the theory stands, conventionally or generally or by the professionals. This is what they say happens. And a lot of the happenings I wouldn't disagree with, but a lot of their causes are, they don't have any. Yeah, they don't state any direct causes, any causal links, no explanation of how exactly you get the products. And it's sort of important to be able to dissect what you're seeing, just to understand it, to understand how it happens. And it's a big missing piece in my opinion, and I think there are answers that are available. They just choose to cling to some, I think, wrong-headed notions of reality.
You have 10 days left for your motor, so that's a nice project for spring break. I'll give you some hints. Keep the friction of your rotor as low as you can. You can't use any oil, of course, that's not allowed.
Like you could catch somebody, they could use Teflon or something and you'd never know about it.
Balance your rotor to the best you can. And try to avoid that the rotor begins to bounce, begins to vibrate. Because when it vibrates, it loses contact with the current when it needs it, so there's no torque. How will we test your motors? We do that with a stroboscope. And I've decided to demonstrate to you how we're going to do that. That's probably the best thing to do. We here have a disc. We're going to rotate the disc.
Seems to me they could come up with a better mechanism, but you know, I guess you don't want to actually touch the motor. You should just slow it down. But it still seems like there ought to be some better way than strobes don't give you exact information.
At 1000 RPM, let's assume that is your motor. And we're going to strobe it with a strobe light until it stands still. In this case, I have set the strobe so that it will stand still, roughly. And the strobe is now going at 500 RPM, and the motor is going at 1000 RPM. So this clearly is not the rotation rate of your motor. In fact, your motor goes twice around between the blinks. And we have no way of knowing that, so we double the frequency. I'm trying to double it now. Double the frequency of the blinking of the strobe light, and now it stands still again. So now we may think that your motor is going 1000 RPM, but we don't know yet. Maybe it's going 2000 RPM, maybe 3000 RPM. So what we're going to do now, we're going to double the frequency. And so we go now with the strobe light to 2000 RPM. And what we see now is we see a double image.
So 2000 RPM is out, and any multiple of 2000 RPM is out. So 4000 is out, 6000 and 8000 is out. But what is not yet out is 3000 and 5000 and 7000. So we would have to test for that. On the other hand, I told you already that this motor is going 1000 RPM, so there's no sense us testing that now. But during the actual contest, of course, we will continue all the way until we are convinced that we have the right RPM for your motor.
And so that's the way we will do it. We will put a little bit of white paint on one side of your rotor. So that's the way it will be done.
So again, it doesn't sound like a great idea. Seems like they could just put a little wire on something and have the metallic thing click, and then they could just count how many clicks per second or something. Seems like there's some better way to do it, but whatever.
If your motor is highly unstable in terms of rotation rate, it will not be easy to get a correct number. I want to talk with you about the heart. Our heart has 4 chambers. It looks sort of like this. The left atrium and the right atrium. Maybe this is why it's called the heart. And here is the left and the right.
I think I'll speed this
ventricle.
up a little.
And here's the aorta. The sole purpose of the heart is to pump blood. About 5 quarts per minute, which is 75 gallons per hour, which is 70 barrels per day, which is about 2 million barrels in 75 years. And it pumps about 70 times per minute. If the blood to your brain stops for about 5 seconds, you lose consciousness. So
all right, this is kind of all stuff we, it gets, this is using analogies for some sort of subject, but no, this is terribly physics related, so I did speed it up a bit.
There's 5 skips of the heartbeat, and you're down on the floor. And 4 minutes later, permanent brain damage. The way the heart works is absolutely mind-boggling. Extremely complicated. Nature had 1 billion years to design it, but nevertheless, it's impressive. Each heart cell is a mini chemical battery.
A lot less than 1 billion, actually. 500 million maybe or something. The first heart, I don't know, 400, but yeah, not 1 billion.
And it pumps ions in or out as it pleases. In the normal state, each heart cell is minus 80 millivolts on the inside relative to the outside. There are some cells which are called pacemaker cells.
All right, the interesting thing to recognize is that this idea of charge is something that does go from the very small little bits to atoms to molecules to whole things. The idea of presenting to the world a kind of radiation, a kind of, you're radiating your negativeness or your positiveness. So I just want to get to that point, that this idea of the monopole, the magnetic monopole, but the idea that you're radiating something, you're taking in from the universe one thing and giving back something mixed differently. So it comes in one way, you filter it, negative bias. That is, you send the positive that way and you send the negative this way. It's just fundamental to the physics of things. But that's what's really happening. It's just a kind of, you become a mirror to one kind of radiation and a deflector of another kind. And even cells are doing it, so to say.
They are located in a very small area, about 1 square millimeter, near the atrium, the right atrium, and they change their potential from minus 80 millivolts to plus 20 millivolts. Now, why they do that is a different story, which I will not address. Once they go to plus 20 millivolts, the neighboring cells follow.
Well, they do it because you got a signal from your brain that's tied right to that little spot. It tells them to do it.
And the wave propagates over the heart. I'll make you a drawing shortly. So the wave first moves over the atrial chambers and then over the ventricle chambers. And when the cells are at plus 20 millivolts inside relative to the outside, they contract. So they form a muscle. The whole heart is one big muscle. And after about 0.2 of a second, the cells return to minus 80 millivolts, and this wave goes from below to above. And then the whole thing waits again for another message from the pacemaker cells. Takes about 1 second, and then the whole process starts all over. Now I want to be more precise. Here is one heart cell. So this is about 10 microns in size. And this cell has 80 millivolts with respect to the outside. So that means it has repelled positive ions. And so the inside is negative, and there is no E field here outside, because if you put a Gaussian surface around here, there is no net charge inside. But there is, of course, a electric field across the walls here, from plus to minus. Now the depolarization, which is the change to the plus 20 millivolt state, starts, and it starts from above. And I would assume now that it is not plus 20, but 0 millivolts, and it's easy to...
Yeah, it's really just going from one level of positive to another level of positive. So it just goes from 80 to 20, not 80 to minus. It doesn't flip. It just depolarizes.
To see. If we have this cell, and the wave is, say, halfway down, and this is now 0 millivolts, then there is no longer minus charge here and no longer plus charge here, because 0 millivolt relative to the outside world. So there's no electric field across here anymore. In other words, what the cell has done, it has moved positive ions back in. But here, the situation is still as it was before. So this is still at your minus 80 millivolts. And if you look now, you have here a minus layer on top of a positive layer. Positive here, minus on top. And that creates an electric field, which has roughly the shape of a electric dipole. This shape. So as the wave goes through the
magnetic dipole.
cells, only then do they create a dipole. And we call this the depolarization.
Kind of neat that he used the same word, depolarization. Yeah, that's what I said.
A little later in time, when this wave has passed, the whole thing is plus 20 millivolts. I show 0 here, but it really goes to plus 20. This is just easier to explain. So that means that now the inside is plus. The positive ions are now inside, negative ions are outside, and the E field here is again.
All right, so it's not positive inside and negative outside. So we just pointed out how it's plus 20 millivolts, so it hasn't switched over. So, you know, I don't know why he said that exactly. You know, he says he's going to use 0, and he didn't even do 0. He did the complete reversal. It's still positive on the outside, but whatever.
0. Now there is the repolarization wave, which comes from below, when it goes back to minus 80 millivolts. And I will again do the same trick that I did before.
All right,
I will just assume
my
the wave
mistake.
is halfway.
My mistake. So he said it was minus 80 millivolts on the inside, and it goes to plus 20. So it's 100 difference in total. Okay, sorry.
That it is not minus 80, but that it is 0 millivolts. So there are no charges here, but the charges here are unchanged. So what do you have now here? You have a minus layer on top of a plus layer. So you have exactly what you had before. So again, you get an electric field, which is an electric dipole field, which has again the same shape.
I would argue you just have a cascade of the pressure. Just moves from one cell to the next cell to the next cell. It doesn't seem that complicated.
So what's going to happen is the depolarization wave is going to run down, leaves behind here the cells at plus 20 millivolts when they are contracted. So this part of the heart has already pumped, and it moves down. And only the cells where the depolarization occurs, that's only the ones on the ring, contribute to that electric dipole field. If there's no wave, it's a sizable fraction of the heart, of the cycle, there is no wave, then there's no electric dipole field. And when the repolarization goes in the other direction, when the heart relaxes because the cells go back to minus 80 millivolts, then again there is an electric dipole field, but only from the cells to which the repolarization wave moves.
So sort of implying that this wave is somehow what we're measuring when you do a cardiogram. Sorry about my voice. I don't know what that is. Hello? Yeah, I don't know. Depressurized. Sort of implying that it's just this line of change is somehow, again, we're back to this idea that you have to have moving charges or something. And I think really all you're really measuring is the fact that there's a change that goes across the whole heart, that your electrical potential changes because the big muscle inside your body has changed its electrical potential. So if you Gaussian surface your whole body, you'd recognize that the heart is now negative 20 versus before when it was positive, well, it's now, yeah, versus positive 20. And that's the change. And that change takes whatever, a half a second to get across your heart. And then it goes back the other way. And that's what you're measuring. You're not measuring the exact line or where it is at any one time. I mean, how far in the process it is at any one time. You're just measuring the fact that it goes from positive to negative and a cycle. So you're just measuring it going across the two sections of your heart.
And you can very easily see that the electric dipole fields of all these cells here support each other. So you get a dipole field from the heart. And so if I make you look at your heart, so this is you, this is your body, your legs, this is your arms, and here is your heart. And there goes this wave. And so here is your electric field that is generated by the wave.
See, I don't think any of that's happening, in the sense I don't think your heart can extend a field that deeply. So I think it's just transmitting the same change of electrical potential in your heart is just leaking into all your other muscles, and they're doing the same thing, and the same as they're transferring some change. But I don't think all this is happening, but whatever. I mean, you're full of salt water, which is conductive.
Is going either depolarization down or repolarization up. But if there's an electric field, there's going to be potential difference between different parts of your body. If you look here at your belly button and you follow this electric field line at your head, there's an E field. The integral E dot dl gives you a potential difference. And so now you see that there are going to be potential differences between the various parts of your body. And that's it.
Yeah, I would highly doubt that 80 millivolts is going to be able to create a field that far away that's going to be in any way significant or readable or any of that stuff, and it really has to travel as an electrical current likely through, again, this fact that we're made out of salt water.
The idea behind an electrocardiogram. Typically, there are 12 electrodes attached to arms, legs, head, and chest to get as much information about the heart as we can. And the maximum potential difference between two electrodes in general is not more than about 2 to 3 millivolts. I'd like to show you a healthy heart cardiogram of a healthy person. I have that here. The time here is about 1 second, and from here to here is about 1 millivolt. The P wave, we call this a P wave, that is observed when the atrium is being depolarized, so when the depolarization wave goes over the atrium. A little later it goes over the ventricle, and you get a larger potential difference because there's more muscle in the ventricle. So that's why this R wave is higher.
It's essentially an electric current is going across your heart, so it's basically happening, and you're picking up some of the residual, the corona discharge, if you want to call it, of that current.
The T wave is the repolarization, when the wave goes back over the ventricles. The dipole field is in the same direction, remember? That's the T wave. It's not known, at least it wasn't known until recently, what causes the U wave. I talked to a heart expert about this, Professor Cohen at MIT, and I was surprised to learn that it's not known what the U wave is about. Not everyone's cardiogram looks as healthy as this one. There is a terrible disease. 400,000 people die of a year in the United States, which is known as ventricular fibrillation, also known as sudden death. The ventricles fire without any message from the pacemaker wave, and there's random non-synchronous depolarization. So the heart doesn't pump anymore. In 5 seconds you lose consciousness on the floor, and in 4 minutes you have permanent brain damage. In hospitals, heart patients are being monitored, and as soon as it's noticed that there's something wrong like this, so severe as the fibrillation, ventricular fibrillation, then they apply electric shock treatment. They have to be fast, you only have a few minutes before you get brain damage. And 3,000 volts is applied, 1 amperes, for about a tenth of a second. Large plates are being used on each side of the chest. And this, of course, is enough to kill the patient. Okay. But it
right, so in the same principles involved. So the electricity travels right through the body. You try to make it go through where the heart is, and some percentage of that electricity will hit all of these cells and force them to synchronize again, where they're not firing against each other, they're all firing together again. And that's the principle. But clearly it's electricity that moves through your body, your tissues, to get to your heart muscle and to neutralize all of their electrical potentials. And it's not any E-wave or anything.
It's a little difference because the patients would have died anyhow. Heart patients can also get synchronization problems, and then they implant a pacemaker. So it's a circuit. And this pacemaker takes over the role from the pacemaker cells. When the heartbeat rate falls below a certain rate, the artificial pacemaker takes over, about 10 milliamperes for half a millisecond, and it does it 60 times per minute. And so it triggers then the depolarization wave. These pacemakers are susceptible to influences from the outside world, and one person's pacemaker stops, for instance, every 10 seconds due to a radar sweep from a police car. It's also possible that you get a built-in defibrillator. In other words, a system that gives you electric shocks when sudden death might otherwise occur. So it senses that something is wrong, that the ventricle is going into fibrillation, and then it applies all by itself 650 volts, about 5.5 milliseconds, up to 5 to 10 amperes. And that's not enough to kill the patient. And the whole idea is...
So the idea is theirs, they don't need as much voltage because it's sticking right on the heart. So it can do it because it's a lot closer to the place it wants to neutralize.
Sort of a wake-up call to the heart to get it back into synchronization, to get this depolarization wave being synchronized again. So clearly, I would like to show now a heart cardiogram of a student, and I prefer to have a healthy one to avoid some difficulties. You feel strong? You're a healthy person? You don't mind volunteering? Tight pants, we have to do something about it. Okay, why don't you sit down? Well, there's nothing like come in. We'll find a way. All right, so we have to attach. We don't have 12 electrodes, we only use 3. And the first one, that's why I was worried about your tight pants. Can you roll them up a little? Okay. Oh, this one goes here. Let's hope that it makes good contact. Now the others go on the arm, and we need very good electrical contact, and therefore we put some conducting grease on there. We'll make it a bit of a mess, but we'll give you a chance later to clean up. So let's first put this one. You're relaxed, right? Yes, of course. So can you roll up your sleeve there? Very good. And maybe you can put this over your arm. Yeah, over your. Yeah, that's good. High up. Oh, man. Oh, boy, you have muscles. All right, just relax. If it hurts a little, though, well, that's the way it is. We need good contact. Okay, now your other arm. Again, a little bit of goopy stuff. Oh, you need another rubber band to put it around your arm, high up. That's good. Yeah. All right. So now it's very important that you relax, because when you start moving, the other muscle cells will also produce electric dipole fields. And that's what we don't want, because then that will be overpowering.
Right, but that's exactly what the whole thing is dependent on anyway, is the fact that the electricity is going to move through all the other cells from the heart is going to change, cause a little bit of twitching and everything, and the body obviously already adjusts to all that, so it's not a big deal.
All right. I'm going to make you take a look at this. Yeah, everything okay? So I'm going to change the light situation so that you can see shortly there what's coming up. Oh man, what a dark, oh gee, look at this. Oh gee. Oh look, I don't see your P wave. But you have an amazing T wave. No, you have an amazing R wave. It looks like your R wave is in the wrong direction. You feel okay though, right? Yeah, I can see a P wave. Well, maybe some people survive without P waves. It's certainly an unusual heart, but if you tell me that you're half T, then I'll take your word for that. I think it would be nice if you show class now, why don't you just stand up for a while, let your other muscles begin to act, and they will see then, just stand up, you will see, move a little bit your arms, move your arms, you see, now you get the electric dipole fields from the other muscles in the body, which contract.
Right, so he's saying they're dipole fields, they're just the electricity moving through the tissues and whatnot, and it's not, yeah, it's not a field of anything, in my opinion.
This is even more interesting than your heart, man. All right, sit down again and let's take it off. And then...
Let's say if it was a field, then I could just put the probe near the skin. I could just put the probe on his, by this chest. I could just put the probe anywhere. And if it was some sort of field, I'd be picking up the field. Why would I need to have the tissue would just be in the way? It'd be superfluous. The field goes right through it. So it's not any field that you're picking up. It's current through conductors.
You can clean up. Looks good. Yeah. Heart cardiograms are not so easy to interpret. But I think you're looking fine. And you feel all right, right? That's important. So thank you very much for volunteering. Very courageous. Yeah, make sure you clean that stuff off. It's water soluble, so it's not so bad. What is your name, by the way? Danny. You were a great Danny.
All right, maybe we'll get back to some physics.
And I want to talk about Aurora Borealis.
I don't know why the volume's so low.
If we have a magnetic field,
it's all the way up. Huh.
And we have a charged particle, let's say, make it plus, and the velocity of that charged particle is in this direction.
Oops, broke it.
And the force on that charged particle, the Lorentz force, equals Q times V cross B. I'm going to decompose this velocity now into one component parallel to the magnetic field, and into a component perpendicular to the magnetic field. So the vectorial sum of these two is V. So I can rewrite this as Q times V parallel plus V perpendicular cross with V. But V parallel cross with V is 0, because the angle is either 0 degrees or 180 degrees, so the sine of the angle is 0. And so the force is exclusively determined by this term, by the perpendicular component. And so what's going to happen, this charged particle is going to circle around, but then it continues to go in this direction with that velocity V parallel. And so you're going to see a pass like this. But by this radius, R, of that circle, that radius, I still remember it from the lecture when we discussed that, that was mv divided by qb, but the v now is of course the perpendicular component divided by qb, and then in this direction, it continues unaltered with the velocity, which is the parallel component.
Whatever. I say, nah, not even close.
Magnetic field of the Earth is not a straight line, but it's curved. And so charged particles can spiral around the magnetic field and follow the magnetic field lines, and they come down on Earth where the magnetic field lines enter, which is near the magnetic poles. The sun emits a plasma. Plasma is highly ionized, electrons and protons. We call it the solar wind. Sometimes it's strong, sometimes it's weak.
So let's understand that that solar wind goes all the way here to the Earth, the plasma. And relating this to the Eddington experiment, the whole idea of gravitational lensing, you know, you have a significant amount of this plasma that's reaching all the way out here. Just imagine how thick it is, just a diameter from the sun, or 2 diameters from the sun, where the Eddington experiment was shooting through. Not likely that you're not hitting electrons.
And when it reaches the Earth, it ionizes the upper atmosphere of the Earth, and then it produces light. The light is very faint, can only be seen at night, and that light is called aurora. And we here call it northern light, but I'm sure that people in the southern hemisphere, they call it southern light.
A kind of corona discharge, in a way.
When the sun is very active, it can be breathtaking, really absolutely fabulous. The aurora can change very fast, on timescales of seconds to minutes. And it is, of course, strongest near the magnetic poles, and so you rarely ever see it in Boston.
And I rarely could care less. So this is another subject that people find it also fascinating. It's like a rainbow. Just doesn't do a damn thing for me.
It can have very bright colors. Red, green, white is the most common. And the color that you will see depends on the energy of the charged particles as they come in, but also depends on whether the nitrogen molecules in the atmosphere or the oxygen molecules are being excited. Also depends on at what height in the atmosphere the ionization occurs. I've seen it quite a few times in my life. I did hiking in the Adirondack where I saw it. I've seen it from Calgary in Canada. But whenever I fly to Europe, the flights are always at night, I always ask for a window seat on the left side of the plane. And that's the reason, so that I can look to the north, and a few times have I seen spectacular aurora from the plane.
Blah, 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 blah.
I want to show you some slides. If you visit the 802 website, I made some links for you to some fabulous slides of aurora. But now I want to show you a few that I have here. Can I have the first slide? This is white aurora, like a nice curtain. Not so uncommon. Change on time scale of minutes to seconds. As I said, you can only see it at night. It's very faint. The next slide. You see another remarkable example of aurora, white aurora. Strange shapes, very unpredictable, and moving. It's like looking at a movie when you actually see aurora. The next one is red aurora. A wonderful curtain coming down. For reasons that are not so easy to understand, the maximum light comes from a ring, which has a radius of about 500 kilometers from the magnetic pole. And the next slide shows you a picture taken from a satellite, which is 3 Earth radii away from the Earth. This is taken in ultraviolet light, and you see beautiful this ring. So this radius is roughly 500 kilometers. And here is one of the magnetic poles. I don't know whether it's the North Pole or the South Magnetic Pole.
Obviously this is not the Earth. It's just a hole that the lens is looking through. This 500 miles obviously is not... Earth is like, you know, a few thousand across.
And the next slide shows you something similar. If you look only at these 4, they are taken 12 minutes apart, again in UV, and you see here a crossbar. I don't know how to explain that crossbar. It's called theta aurora. Obviously why theta goes without saying, right? Amazing. And this is sort of, these are 12 minutes apart, so that gives you also an idea how fast this can change. Here it's very dark and here it's very bright. So the changes are quite dramatic.
The bar looks like it just moves across, so it looks like it's just a very high intensity little wavelet or whatever. Just a band of energy. So, I mean, if you look at the images, it does move across.
Now, I want to talk about superconductivity.
Okay, new
Superconductivity
good.
Was discovered by a Dutch physicist. His name was Kamerlingh Onnes.
So again, has to point out the Dutch guy.
And he discovered that if you cool mercury to something like 4 degrees Kelvin, he used liquid helium for that. In fact, he actually discovered how to make liquid helium. That was the incredible thing. And then he used the liquid helium to cool down substances, among them mercury. And he discovered that mercury would lose completely all its resistivity. So the electrical resistance would go down to 0. And he got the Nobel Prize for that in 1913. You can only understand superconductivity with quantum mechanics. And even quantum mechanics has a major problem nowadays to understand all the phenomenon about superconductivity.
Well, I would argue that some of it's kind of intuitive. You know, you're just saying you're isolating all the wrong kind of movement in a substance. So you're making the pathways extremely efficient. No. Yeah. But, and so the resistance is about impurities usually too, but, you know, I don't know why they become irrelevant, but when you have something like mercury, you probably have very little impurities in the mercury.
The problem started in 1986 when two scientists in Zurich, Müller and Bednoorts, discovered that certain alloys can be made superconducting at a temperature as high as 35 degrees Kelvin. And theorists earlier had proven that it was impossible to ever get superconductivity at 35 degrees Kelvin. And so this was such a splash in the community that these guys got a Nobel Prize within 1 year. In 1987, they got a Nobel Prize. I don't think there's any other example that I recall.
So I guess, you know, I would just add to the conversation a little bit that we're talking about heat being a problem for most substances, but obviously everything has a different freezing temperature. You know, we think of ice and that temperature as being cold, but to other substances that's warm and they're still liquid. So it sort of just depends on when the molecules, the atoms, stop jiggling in eccentric ways. And I guess for different substances that would be a different temperature.
Well, by a discovery was made, and within 1 year the Nobel Prize was awarded. And theory still cannot explain today fully why there is what's called high temperature superconductivity. The record today, I checked that yesterday with Professor Lee at MIT, the record is now 135 degrees Kelvin. So certain alloys can be made superconducting at 135 degrees Kelvin.
Yeah, which is still like 50 below zero or something.
And since you probably know that liquid nitrogen has a temperature of 77 degrees Kelvin, anyone can now play nowadays with superconducting materials, even high schools, because liquid nitrogen is very easy to come by. If you make power lines out of superconducting material, there would be no loss of energy. People are thinking about that. You can imagine how costly it might be. But in principle, you could transport electric energy without any loss, without any ohmic losses. No.
Yeah, ohmic losses, but those aren't the losses that are costing you the most anyway. It's the corona discharge that's the problem.
So I square R, because R is 0. Also, if you have 0 resistance in a material, you can run extremely high current through it. And you can therefore get very strong magnetic fields.
Right, but there's a limit. So again, it just enhances the conductivity. They really shouldn't call it, they shouldn't imply that you've now made this thing capable of carrying any amount of current possible, because it's still a limit to how much you can carry before it starts to melt.
And using superconducting coils, you can get very strong magnetic fields, and these colliders that we talked about earlier, these atom smashers, like we have at Fermilab and in Geneva, they are going to make use of superconducting coils to get magnetic fields as high as 6 Tesla or so, even higher.
And the thing, that's what blew up, that's what broke, you know, that's why they had to take 3 years to fix it, is because that's the part that broke.
No electric field can exist in a superconductor. And you can very easily see that, because if there were an electric field, if this is a superconductor, and there is an electric field, say, in this direction, there would be a potential difference over the superconductor. And Ohm's law, V equals IR, tells you then immediately that if this is not 0, but if this is 0, that I would go to infinity. So you cannot have any electric field in a superconductor.
You don't have one in anything anyway, so... and obviously you can't transmit the electricity at any supersonic speed, so it can still only go at the speed of light. So there's still limitations built into the constants.
If I approach a superconducting disk or material with a magnet, say this is the North Pole and this is the South Pole, so we have a magnetic field configuration roughly like so. If I approach this superconductor...
Now what this is sort of going to be an example of, I'll probably do this whole video, is the fact that if you're a superconductor, again, you've gotten rid of all the noise. So in a sense, it's like a perfect mirror. And so whatever you put on top of it, you'll get a perfect mirror reflection, because it's not doing any of the Brownian motion thing anymore. It's not doing all this jittering that screws it up in other circumstances. So the reason why you can't do these kind of things with regular experiments is you can't create a perfect enough reflection of a magnetic field to levitate. It'll cause all kinds of other disturbances, and it'll cause the magnet to flip, of course.
Material, then the EMF generated in here because of Faraday's law, because there's a change in magnetic flux coming off, that EMF must remain zero, because you cannot have an electric field inside the superconductor. And this, of course, is IR.
So again, there's no field inside a conductor. It's the transfer of the pressure or the voltage is atom to atom to atom to atom. That's why conductors have to be made out of something that has atoms in it. So there's no field that's transferring the energy. The energy is being transferred from one atom to another, and the energy is in the form of pressure between electrons. So the electrons hit each other. When they hit each other, they hit with a certain amount of violence. And if this one hits with 20 and this one hits with 80, then this one's going to end up being 60 or 50, and this one's going to be 50. They're going to neutralize the differences between them. And that's the migration of electricity.
Also zero. So I now can have any value, completely legitimate. So you can have a huge current inside the superconductor, but no EMF. And so as you approach with this magnet, eddy currents are going to run inside the superconductor.
All right, so again, as I've stated before, the eddy currents aren't what's creating the magnetism. The magnetism is created by the very fact that you're pressurizing the electrons. So you're coming at it with the north end, that means you're going to pressurize the electrons. If you came with the south end, you're going to depressurize them, essentially. And that makes the atoms itself, the atom itself, into the exact same pole of the magnet. So, and it's going to just reflect perfectly back at the other magnet exactly what it's getting, because it doesn't have a bunch of motion in it. So because you've taken all the erratic motion out of it, it's going to reflect perfectly back at the other magnet. So it's going to levitate it perfectly, because every little bit of south is going to create a south reflection, every bit of north is going to create a north reflection, and it's just going to sit on top of that perfect reflection.
Such a way that the phi dt, the flux change in here,
the phi dt. I hate the way they say this stuff. I don't know. That's not. Is that what that is? That's a d phi with a little b, then a dt, and it's not a multiply. It's a divide. So shouldn't you call it something else? I hate when they do that. I mean, they have a special word for some kind of thing, and this is not. You know. So I mean, the d is obviously has something to do with distance and time, and that stupid slashy epsilon-y thing has some constant value, and I don't know why it has a b below it.
It's always zero. And so these eddy currents will flow to never allow any magnetic flux, because there was no magnetic flux to start with when the magnet was high up, so there can never be any change.
All right, so it's just wrong. I mean, there's no, the magnet doesn't cause a current. First, the first thing it does is it changes the pressure of the electrons. It changes the atoms sitting right there on the surface. And then they'll try to get rid of this pressure that you're imposing on them if they're conductors. But the fact is, that's what you're doing first. And doing that is all you need to do to create the charge response.
And so the eddy currents create a magnetic field themselves, which if you vectorially add them to this magnetic field, will always make sure that there is no net magnetic field inside the superconductor. And so if you...
There's no net magnetic field between the two is the whole point. The point is it's an exact reflection. So yes, if you add up what the response by the superconductor is going to be, it's going to have exactly the same response as came into it, because it's going to create exactly a mirror image of what's coming in at it. So it's just saying the superconductor is a mirror, and it will be created into a mirror. Obviously it's not a mirror until you impose on it with a field, and when you show it a field, it turns exactly the same color, like a chameleon. It sees the environment, so to speak, and it responds to the environment by turning exactly the same color.
Now make a drawing of the two fields, the one that is produced by the eddy currents and the one that is produced by the magnet. When the magnet comes very close, so here is north and here is south, and here is your superconductor, then the superposition of those two fields then effectively comes down to the fact that this magnetic field is completely repelled. It's another way of looking at it. You get a squeeze field.
Yeah, well, there's no, this one gets repelled and the other one doesn't. They're both repelling each other. So it's north-south, north-south. The north ends are going to face each other. If you tilt the magnet, then the south will face the south. Like I said, it's just a mirror image is the way to think of it. It's just mirroring exactly the force you throw at it. It throws back at you.
But there is a superposition of two magnetic fields, one produced by the eddy currents and one from the magnet. And whenever you have here such a squeezed magnetic field, there is magnetic pressure. We know why there is magnetic pressure, because north and north poles repel each other.
Right, but you don't have any explanation for why. So again, we know, we don't know. You're incredibly uninformed, and you don't even have reasonable speculations of what the real mitigating force is, what exactly is pushing the magnets.
We never express that in terms of a quantity. And the magnetic pressure equals B squared, which is the magnetic field strength, divided by, is it 2? Yeah, 2 mu 0.
Well, you're going to have to deal with the fact that there's gravity involved, and so somewhere in here there's got to be some recognition that depending on how you set up this experiment, gravity is pushing the magnet down.
0 divided by 2 mu 0. I'll get back to this a little later in the lecture. And this is pressure, so this is in newtons per square meter.
And so the B field squared, so that's just basically acknowledging that you're going to create a mirror image, and the two fields are not going to just be additive, they're going to be they're going to keep inducing that, they're going to keep reflecting.
This is not entirely new, this idea of pressure, because you may have seen at people's desks, a nice conversation piece, you have here a magnet, and you have here a magnet, and this is a wooden stick, there's a hole in here, and there's a hole in here, this is North Pole, South Pole, North Pole, South Pole, and they repel each other. That's magnetic pressure, it's the same thing. And if you drew the magnetic field configurations here, go like this, that's a magnetic field from this magnet, and this would be...
Again, the magnetic fields do not bend, so none of that happens. You don't bend magnetic fields, the magnetic force. It's rays of force, and those are what you would see with a compass. They're what you would see what a magnet would do in these different positions. It has nothing to do with what the actual force is doing, which is going straight between the up and down, right between the two things. The force is not bending
the magnetic field from that magnet. You get the same idea. You get magnetic pressure there.
You would not measure, like if two magnets are floating on a stick like that, you're not going to measure more magnetism flowing out of the sides here or something, because the two magnets are squishing the magnetism out. There's not going to be any currents or any flow or any extra magnetism or anything flowing out. So those lines are just a deception. They're not the real path. They're not what the force is doing. It's what an imperfect measuring tool will tell you the overall field looks like at those locations. How much energy is hitting from the red end and how much energy is hitting from the black end. But it's not going to tell you what's happening between those two magnets in terms of where the force is actually moving. The force is moving between them.
If I rotate this magnet here, so first of all the magnet is repelled, which is in a way a form of levitation. I'm going to show you that. The magnet is just pushed up by a superconductor, the way you can look at it. But if you start rotating it, for instance, around with the south pole here, or the south pole there, or the north pole there, the eddy currents will instantaneously adjust to always repel that magnet.
Well, it's not instantaneous, it's the speed of light. The trick is that there might be some motion that'll happen all the time just because you can't really make this superconductor perfect. It's still going to be probably a little bit flawed, and those little flaws will show up in probably a little bit of rotation.
So even if you rotate it, it would still hang there, levitated, rotating. Well, it's not so easy to understand why the whole thing is so very stable, as you will shortly see. It's quite stable. So I'm going to show you there this superconducting idea. I first have to top it off with some liquid nitrogen, so let me do that when we still have full light. Oh boy. Good. So I have to top it off. And this disc, which is about an inch in diameter, going to be superconducting. I can even tell you what kind of material it is.
Good.
It is a copper oxide mixed with yttrium and barium, and it becomes superconducting at 90 degrees Kelvin, and liquid nitrogen is 77 degrees. So we're going to put a small
No, it's a metal alloy.
magnet on top, which we will levitate. And for that, we're going to have the following light situation.
Paramagnetic materials, and I think barium might be diamagnetic, but anyway, no ferrous material involved.
And
so you're clearly going to get a repulsive response, not a attractive response. If it was ferrous material, you're going to have magnetic domains. They're going to line up, and you're going to end up with dipoles, and you're going to end up with mixed pressure. With paramagnetic, you're creating atoms that will actually be magnetic monopoles. So you're either going to create a bunch of, on the surface, a bunch of north magnets or a bunch of south magnets right on the surface.
of course you want to see it also, don't you?
Poles, south poles of a magnet, monopoles. You're going to create magnetic monopoles.
And you want some light. So there you see the disk, which should be superconducting now. And here comes my little magnet, so there is no magnetic flux going through there. It itself is not a magnet. But now I'm going to come close with a magnet, and the eddy currents go nuts in there, and it just floats on top.
So you can see there is a little move there. Yeah, you can see it now.
It's amazing, isn't it?
A little bit of movement.
So this is magnetic levitation, and you can rotate it around, and the eddy currents adjust instantaneously.
Again, it's speed of light. Okay, yes, okay, technically, you know, just being technical, it obviously doesn't happen instantaneously, and so there is limitations to systems like this because it doesn't happen instantaneously, and if you do certain things, you'll break the system because it's not instantaneous.
And there it is. Yeah, you've all seen.
So it's just, like I said, it's just because the superconductor is creating a very, very good mirror image of the force hitting it. It's reflecting it quite perfectly. And by perfectly reflecting it, no matter where you put the magnet, it's going to keep getting exactly what it's giving back as a push force, compensating for gravity.
Seen it? Clear enough? Okay, let me get the rescue my magnet. Imagine in the days of Caroling Honest, it took 4 degrees Kelvin to have anything superconductive. And now you can do it as easy as that. There are other forms of magnetic levitation. One is going to be very promising in our economy, we hope, and that is magnetic levitation can be used for trains. If you have a magnet and you move it fast over a conducting surface, then you also get levitation. You have to
paramagnetic conducting surface.
Move it though. Whereas there you don't have to move it. See, if you let that magnet just go, if you don't move it anymore, then there is an eddy current going on. But the eddy current never dissipates any heat. There's no I square R because R is 0. So you never lose the eddy current.
Yeah, well, it's not about losing the eddy current. Again, it's just about the fact that there's nothing disturbing the matrix of atoms, and the atoms are basically going to turn exactly what they're getting. They're going to turn into that effectively. When you push pressure on them, you push the electrons closer to the proton. That means you mask more of the proton's energy, and you create a monopole of the atom. The atom now has the appearance of being negatively charged, just like the charge coming at it. And the charges reflect, and that's it. The two surfaces, the magnet surface is going to reflect back exactly the energy, and they're going to do it back and forth, ping pong balls trapped, and they're just going to keep pushing exactly with whatever force is hitting them.
That's different with what is coming now. Now I have a magnet. Here is north and here is south. So we have a magnetic field sort of like this. And I'm going to move it over a plate, over a conducting plate. And I'll put the plate here. And as it comes over this conducting plate, the magnetic flux through that plate will change. Mr. Faraday says, actually it's Mr. Lenz who says, I don't like that. And so they're going to run an eddy current in here. And the eddy current will undoubtedly go in this direction as it comes over here. And this current ring now.
So just understand what they're saying. You know, if something's moving very fast, they're saying that somehow this current somehow keeps currenting, and that there has enough speed to do this roundy thing, plus move in the direction, and then somehow creating dipoles all the way around that ring somehow that are creating the radiation, because that's the argument here, is that the magnetism is happening on conductors. When you move a current through, the magnetic field is coming radial out of the side here. That means the little magnets are plus, minus, plus, minus, plus, minus going around the rim. And it's that magnetic field that creates the effect. So they're kind of arguing that somehow in the material there's a bunch of these little magnets that are all turning. No, no way. No way that's happening.
Will produce a magnetic field in this direction. And look what you have. You have again, this is the North Pole of this.
It's almost like they're arguing a solenoid is being created, and obviously the density of the material isn't enough to create any solenoid. So you can't get a whole bunch of reaction. All you're doing is compressing essentially the surface. You can think of it that way. You're compressing the surface, and when you compress the surface, it turns into the exact force that you use to compress it. And if you expand the surface, it creates the exact force that expanded it. So, you know, it's that simple. It mirror images. It just doesn't mirror image as good as a superconductor. So the so you still have to have rails or something to keep the thing on track, because it can't just perfectly levitate, or it's got to have something to keep it on the track. But you remove all the friction, obviously, so there's a huge advantage. But it's doing exactly what the superconductor is doing in terms of it's creating the force, and the only difference is it doesn't create a force that's perfect enough for the magnets not to go all wobbly.
Eddy current, and this is the South Pole. North Pole repels North Pole. And so if this has a high enough speed so that the change of the magnetic flux, the d-phi-dt, is high enough, the train can float. Tens of tons of weight can be made to float. And the reason why in this case the train has to keep going, that if the train stops, the eddy current will die out. There's no longer the d-phi-dt, but there is resistance in this conductor. And so you get ohmic dissipation, you get I square R, you get heat in here.
Now what you get is time for the compression to move through the conductor. So if you stop, the compression equalizes and just moves out of that space. So it's just the fact that the conductor takes a while to move the pressure that you're taking advantage of. So you've created the opposite field, but the opposite field's only going to last as long as it's going to take for it to leak out. And it does leak.
And so then the train will just plunge down. And that's not the case with the superconductor, because you don't dissipate any heat in the superconductor because the superconductor has no resistance. So the idea is the same, but you see now why you have to keep this one going and why there you don't. And so again, you get a squeezed magnetic field like you have there. And so you get the...
Yeah, well, the superconductor spreads, I suppose, the pressure much quicker, you could argue. I mean, I don't really have a great answer for that off the top of my head. Maybe that's why the magnet still rotates, is because it's still changing the field. So the field does actually die. The magnet falls a little bit. When it falls a little bit, it's again repressurizing. Then there's a response. So maybe that's why the magnet tumbles, is the very reason that it's just doing it very quickly, responding to the fact that the field actually does die. The current actually does move through the superconductor, that the pressure dissipates, and it has to repressurize it. So it goes to neutral, it repressurizes, goes to neutral, it repressurizes. So in a sense, it's a mirror image that might be blinking, you know, blink, 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 going at a very high frequency. It's blinking back at the magnet.
Magnetic pressure. Japan and Germany are really the leaders in the world in the technology of maglevs. That's what these trains are called. The United States is trying to catch up. There's an enormous reduction in friction if you can have a train that is not in contact with the rails. In fact, speeds have been recorded up to 340 miles per hour. Both Germany and Japan have test trains, prototypes, in operation. The United States has made a commitment to build a maglev train to go from Washington, D.C. back and forth to Baltimore, should be ready in the year 2007. The costs per mile are about $30 million per mile. Now that may strike as high, but keep in mind that if you build a four-way highway, that's also $30 million per mile. So it's no more expensive than a four-way.
Yeah, but a four-way highway carries, in terms of passengers and cargo and whatnot, a hell of a lot more per square foot per hour than your train is going to.
Highway. And again, when you visit the 802 website, I made several links to maglev sites. I advise you to take a look. Now there is a third form of magnetic levitation, whereby we don't need any speed and we don't need any superconductors, but we use AC, we use alternating current. And that's also easy to see now. Here is such a coil, and we run AC through it. So at one particular moment in time, let's say the magnetic field is like so, and maybe is increasing. And then of course the magnetic field turns around, up, down, because it's AC. And now I have here a conducting plate. And I put this above this plate. But now I have this
paramagnetic again. Let's just make sure we keep saying paramagnetic plate.
Continuous magnetic field change. So I have a continuous change of magnetic flux in that plate. So as this magnetic flux, as the B field down is increasing, you're going to get an eddy current running in this direction, which will create a magnetic field in that direction. And you're back where you were. You again have North Pole, South Pole, South Pole. So again...
So it's the same old problem. You really have to be able to pressurize something. You have to let it go unpressurized before you can pressurize, and unpressurize, pressurize, unpressurize. And that's what the AC current will take advantage of, is just the time delay and the fact that the pressure doesn't move through the conductor quick enough before there's another change.
The eddy current in the conducting plate is responsible for a magnetic field, and the two repel each other.
So a little later in time, the magnetic field strength will decrease. When that happens, the eddy current will reverse direction and the two will attract each other. And so you...
I guess the interesting thing to do, you could do lots of interesting experiments, but I guess it would be to take two of those coils and invert them on a stick, you know, and just levitate them, and you get the idea. And then maybe you could count or see, you know, by putting a plate in between that. That would be interesting, what it does.
think now it seems quite reasonable that half the time they will attract each other and the other half the time they will repel each other. That, however, is not the case. There will be a net repelling force. And why that is, I will explain to you during the next lecture. But I want to demonstrate it now.
Well, I don't think that needs to be explained, just because you're obviously just keep converting the paramagnetism into the opposite. It'll always respond by doing exactly the opposite of what you're imposing. You're always just kind of turning the surface into a mirror for the force.
If here, such a coil, about an area of about 1 square foot, I can simply run 110 volts, 60 hertz AC. I switch this, turn this on, just goes into 110 volt outlet, and I increase the current, starts to float. No high-speed train, nothing superconducting. What do you think will happen when I turn it over? Excuse me? Of course it will float again. The eddy currents just adjust themselves at any moment in time, and they will always make it float. So this is another interesting form of magnetic levitation. So we have the superconducting way, whereby there is no dissipation in the disk. So those currents never die out. Then you have...
Well, you'd say that in a sense they have to die out quicker, you know, because they can spread through the whole material quicker because it's a superconductor. So that part doesn't make much sense either. Why are the currents limited to this? Why are they just doing this? Why can't they just go into the entire material?
The case of the train, if I call that the train, the magnetic levitation, whereby you have to keep the speed going, because if you don't have the speed, then you don't have enough magnetic flux changes in the surface, and so you don't have the eddy currents. The eddy currents will die. You get...
The flux changes are only needed to compensate for the fact that the surface is, once it's stagnant, once you've pressurized it, it stays pressurized. It's a better way to, it's probably a better way to say that. All right, well, I'll save it for another video. But it just has to do with how much of it's dissipated and how quickly.
Heat dissipation. And then there is the third case here, whereby you simply have a changing magnetic field in the coil is AC, which then creates a changing eddy currents. So now we come to the levitation of a woman. How do we levitate a woman? Well, the secret must be in that equation. P is B squared divided by 2 mu 0. We have a coil which is about 1 square foot, so the area of that coil is about 0.1 square meters. And so our goal was that we should be able to lift, let's say, a 200-pounder to give ourselves a little bit of leeway. And so we calculated that if the magnetic field...
Yeah, it's definitely not a 200-pounder.
P is about 1,500...
I mean, I don't know why you wouldn't just use the 100-pound.
Gauss, which is about 0.15 Tesla. But we would get very close. We know that mu 0 is 4 pi times 10 to the minus 7 in SI units. And so you can calculate now what the force is.
So mu 0, again, is a constant. They never, you know, but they never just write it in as a constant. So why did they bother with this 4 pi times 10 to the minus 7th? Why don't you just give us the real number times 10 to the whatever minus 7?
On this area. The force is, of course, the pressure times the area, assuming that the magnetic field is uniform. And so you're going to get that this force is going to be B squared, which is 0.15 squared, divided by 2, divided by 4 pi.
Somehow this math has to come up with the point that this coil couldn't barely lift a turtle.
Times 10 to the 7th, multiplied by the area, which is 0.1 square meter, and you find that this is about 900 newtons. 90 kilograms. As I said, a 200-pounder. Then we tried to get this magnetic field, and believe me, Marcos and I and Bill, we really tried. But there was a problem, because we needed enormously high currents to get this magnetic field. And at these very high currents, our circuit breakers would go every time. So we called up the physical plant, and they said, yeah, what do you expect, man? You need several hundred amperes. You think we can get several hundred amperes out of this system? You have to redesign MIT for that. So it was very disappointing for us. So the best we could do with a strong current.
Well, you think you'd figure out how to do it with capacitors or something, batteries.
That we could generate, we could only get a magnetic field of about 350 Gauss, which is 4 times lower. And the tragedy has it that the magnetic pressure goes with B squared. So that makes it 16 times lower. So the 200-pounder now becomes a 12-pounder. So that's the reason why, when some women wrote me a very nice email yesterday, because they volunteered, why I had to say thanks, but no thanks. But I want to keep my promise. I said I was going to levitate a woman, and I will.
Some more of the shtick. Yes, the shtick.
And here she is. And as far as we know, it is a woman.
Very classy.
Okay. Give her some room. She deserves. You ready for that? And there she goes. I levitated a woman. Have a great spring break.
Okay. So, there, we got one whole video in this episode, for better or worse. Anyway, and such. It's probably better just to say superconductivity was in here, so it's probably a more important subject. And such. Okay, sorry, just collecting a title. Yeah, so I think that's all that needs to be said. So anyway, yeah, so eventually, you know, I'll try to diagram more precisely, you know, this whole idea of what's happening to atoms, and then how atoms have to, you know, spread whatever happens to them. They spread to all the other atoms, and that's the real mechanism here. And that obviously, see, it's sort of like, look, when you sort of know when you're pressurizing something on the edges, let's say you're sending down a field of pressure. And so you pressurize the things down here. Part of the problem is the things on these outside edges are being pushed this way. And so they can't go against the stream to allow the current to keep moving. So the only stuff that can really interact is the stuff caught in that pool where you have left water. So in a sense, you can understand when you bring the field down, you can trap something here in the middle, and the stuff on the outside will be pushed out. And so that's one of the factors that creates a limitation here, in terms of how the atoms rebound or neutralize the pressure. So they can only neutralize it with the bottom atoms, atoms below them, not ones on the surface. But yeah, it's lots of lots of, you know, it's lots of subtleties to this subject. But I would argue that something that can be understood to be not realistic is the idea that this has something to do with you just make a current go around, and somehow you're going to create powerful magnetism coming back, enough to lift a train. I mean, people should be able to realize that can't be exactly what's happening. So anyway, till the next time and such.